Hi guys, welcome to Learning Electronics Repair. I have some PCBs here. These are from PCBWay.com, who sponsor videos on learning electronics repair. And this is the MultiLOAD project. So this is revision 0 of the PCB. This is a project I was working on with Detlef Amend. And it's an upgrade of a USB load project that was already on PCBWay. I'll link to the original video so you can see the original project that we were working with. So basically, our upgrade to this consists of a few things. The original project had one transistor, one power transistor, and could load about 35 watts. This version you can see has 4, okay, some very heavy tracks going between them on both sides, okay, and this should be able to load maybe up to 140 watts. That's the idea. It's a very simple thing. As it stands, there's no microcontroller on here. It uses a dual op amp to create the constant current source, a simple potentiometer on the end, 10k pot, you can adjust the current. So this has a USB-A plug on it. You connect that to your USB power supply and you can load it, okay. Now, as it stands, there was no measurement on here, no meter, so I was connecting this to a USB analyzer so I could see the current that we were loading on the USB power supply. As well as upgrading the current load, the wattage this can actually handle, we've added a few connectors. So you'll see this one here says display board. So Detlef is currently working on a little adapter that plugs on here or use a small microcontroller, a LED or similar display, and this will read out the voltage, the current and the wattage. Those are the main things we want to know when we're using the load, and because of that we no longer need to use the USB analyzer in most cases. The second thing we've added, and we can play around with this today, is this USB PD decoy. So this little board will connect onto here where it says decoy, okay. This will then give you two things. First of all, it has a USB-C connector, so we can use it with USB-C. And secondly, the little switch here will allow you to control a power supply which has PD. So you can switch it from 5 volts, 9 volts, 20 volts, whatever voltage the thing will supply, 12 volts, and that will allow you to switch between the various voltages. We can use this in conjunction with the USB-A connector, so you can connect the USB-A. If you do that, the load will work in the same way. You just don't have the PD because PD is for USB-C. If you connect this, then you have the PD. And both will work with the display board, so we can actually look at the parameters, how much current and wattage we are taking from our power supply. So that's where we're up to so far. We can do everything but the display board today. But to do the display board, we have to have this working, and then we can start playing around with the firmware to get that to work as we wish. These large holes here are actually for these type of connectors. So these are the banana or 4mm sockets. You see they fit through the board here. So that means we can actually use this as a general purpose load, not just for USB. So that's another use for the device. I need some sort of heat dissipation for this. So I found this. This is off a scrap mixer amplifier. It's quite a nice heat sink. I can bolt a fan to the back of it if I wish. I'm sure I'll find some way to do that because there's some holes at the side which can support a little bracket, maybe for 2 fans on there, okay. I'm sure with a little bit of voltage regulation or a little controller, I can make those fans work on any input voltage we're likely to use on this load. And we can wire it in such a way that they draw current through the display, so when the fans are running, we can see what current they're drawing as well, so it doesn't skew the readings. So that's the general idea. The output transistor I can bolt onto here. I have some connectors which will fit into here, all along here to connect to the output transistors. So I just need to find a good way to fit all this together, and now we can play with it. You can see the board that we made is clearly marked, so where the transistors go, all the resistors, capacitors have the values marked on them. We can clearly see the direction for fitting the TL431. This is the voltage reference for the chip. So this is going to be quite simple to put together. So I won't make you sit and watch me solder components into a board. I'm sure you all know how to do that, and if not, I have some soldering tutorials. So I'll get this thing put together, and then we get on to the interesting things, which is to actually test it. Here is the original project on PCBWay. It's a very simple thing. It was uploaded by this guy, Easy One, from Germany. He has a YouTube channel. We had a look at this on previous videos. I will link them in the description to this one. So this is one of the shared projects on PCBWay. That means that the author has uploaded the Gerber file to create the PCB. He will also give you the schematics and everything else to go with it. And once that's uploaded, if you then want to build any of these, you just add them to the cart and the author gets 10% commission. Ordering PCBs from PCBWay is very inexpensive. They ship to just about anywhere in the world. And for a project like this, the minimum order is 5 PCBs, which will cost you $5. And the shipping, well, to Spain, where I'm located, is about $4.50 or thereabout. So the total cost is actually very low. You can order 5 PCBs for less than $10. And better than that, if you go into the video description, you will find a special voucher code. If you are setting up a new account on PCBWay, use the voucher code and you will get $5 off your first order. So 5 of these PCBs is just going to cost you the postage. I've put our prototype together now, so let's have a look. And here it is. You can see I've bolted the 4 transistors to this heatsink. They fitted quite nicely. I got extremely lucky because it just turned out that where the little thermal switch was bolted on, once I removed that, it was exactly the correct spacing for the holes on the PCB. That was by accident. Now this area of the PCB where this is bolted through has a ground plane. It's possible that the metal will wear away at the solder mask, so I could get a connection from ground to the heatsink. So what I've done is I've isolated all the transistors. So you can see the transistors have little washers underneath them. That's the white ring there, together with the little heat conducting washer underneath. This gives a good thermal transfer, but it actually isolates the tab of the transistor, which is the collector, which will have the supply voltage on coming from the USB, whatever it is, 5 volts up to 20, depending what sort of PD power supply we're testing. And we don't really want the tab to short to the heatsink. Now, all the transistors are actually in parallel, so that wouldn't be a problem as such, apart from the heatsink would be at whatever voltages are coming from the USB, but these USB supplies or anything you've got plugged into the banana sockets are basically isolated from the mains, so it wouldn't really be a problem to have this floating at some voltage. The only problem being if I get a short from the ground plane via the fact I've bolted the PCB to it. So that's why I actually put the insulating washers under there. This is ready to test then. I could have put some heat shrink on all the transistor legs, but being a prototype, I want to poke around this. Yes, I can poke around on here, but if something goes wrong, I want to change a transistor. It was much easier if I do it like this. I can solder the wires easily and unsolder anything that may inadvertently go bang, as sometimes happens on this channel. So let's connect our USB analyzer. We'll connect a supply and then let's see if the load actually works. I've connected my USB analyzer because at the moment I don't have the metering module on this. This is the next thing we're actually going to do to complete this project. I've connected it to the normal USB at the moment, so it's not on the little decoy, but we can try that afterwards. So I have a USB-C, you can see the blue lead, the other end's there. This is a cheap USB charger. It is PD, but I think it only does 5 volts, 9 volts and 12 volts. So we'll plug that in, we'll switch this on, and let's see what it actually does. Well, there's power on it, okay, and we can see that it is actually drawing a little bit of power. And that's increasing as I turn this up, okay, so we just zoom down a little bit. At the moment we have 2 watts of power, 2.3 watts. If I turn this up, it's actually decreasing, so I actually have it back to front. Okay, so 0.045. Up to 2 watts at the moment. Apart from this working back to front, if you like, with the control, we have a problem with this as well, another problem. So if we turn the load up, I can get about half an amp out of this I mentioned, but I should be able to get more out of it than that. So what I'm going to do is I'm going to connect the original version that we have. So this is the one from PCBWay. Now the author did not publish a schematic for it, so at one point on a previous video, Detlef and myself reverse engineered it. I think we did actually publish that, so I'll have a look for you. If so, I will link it. But we reverse engineered this obviously so we can make our own PCBs, and I think we might have messed this up. But first of all, let's just make sure that the power supply I'm connecting to the USB PD power supply actually works properly. Okay, so here is the original version. It's modified slightly to use 2 transistors on a heatsink. To do that, I connected another 1K resistor down here to drive the base of the second transistor, and that's because with one transistor I noticed it was getting rather hot. So let's power this up and let's have a look. Okay, we're on. I believe the control actually works the right way round on this one, so you can see at the moment we're drawing a very small amount of current, 0.002 amps, so a couple of milliamps. And I'm already up at 1 amp, and I'll just keep turning this up. So this will load up to 3 amps, and yet the other one will only go to 0.5 amps. My first suspicion is that we've messed up the schematic somewhere when we reverse engineered this. But I do have another thought, and that is that maybe the problem is that I'm using 4 transistors on the output rather than 2. I mean, we know it works with 2. So let's just disconnect 2 of the transistors first. Let's just eliminate that possibility before I spend time trying to work out if we've made a mistake and where it is. So to do that, it's going to be quite simple. I'm just going to disconnect 2 of the transistors. I could just disconnect the base, but then it would be floating, so in fairness, I don't think with a bipolar transistor it would cause a problem, but I'll actually disconnect the base and collector on 2 of them. Okay, so we have that one disconnected. I'll disconnect the base as well, and the same with the next one. I can leave the emitter connected to ground. It's not doing anything, it's the only terminal that's actually connected now. So let's just do that. Hopefully you can see now why I designed this way, so it was easy to play around with things like this when there's something wrong. So we have 2 transistors. I'll connect the load. Let's switch on. Again, just press a button. And we have 0.45 of an amp. So It's the same, actually. Disconnecting two of the transistors didn't make any difference. So let's have a look at the schematic and then see if we can take some measurements. But I do suspect the problem will be an error when we reverse engineer the other one. And here is the schematic that we reverse engineered. So we have the dual op amp, and then we have the transistor. You'll see this is actually what's called a Darlington transistor, so it's effectively two transistors in one package connected like so. This basically increases the gain, so you need a very small base current to turn the transistor on. That's why I'm quite confident that we can have 4 transistors all driven from the same op amp. I'm just using a separate 1K resistor from here. So imagine another 1K here, and then another one of the output transistors and so on. So there are 4 of them. And you'll see all the current that flows through the 4 transistors flows through this resistor, 50 milliohms to ground. Okay, the other end of the transistor, this is VCC. This is the input from the USB or other power supply that you want to load. Now let's look at how this works, because it's quite simple and it looks okay just looking at this. So we'll start with this. This is a TL431. This is a voltage reference. And when you connect a TL431 like this, with the cathode and the ref connected together, anode to ground, what actually happens is you get a 2.5 volt reference. So the voltage here on pin 5 of the op amp is 2.5, fixed, no matter what the supply voltage is, up to the limit of the reference. I think that's 35, 40 volts, something like that. I'm sure the op amp would give up before that, but we put in 5 volts, that's fine, this should work. So we have a fixed voltage on here, which basically means the op amp will try to take the inverted input pin 6 to the same voltage as pin 5. So if this circuit is working, then pin 5 and pin 6 of this op amp should have the same voltage on them. Okay. How does the op amp put the same voltage on pin 6 as pin 5? Because that's what an op amp does. It will always try to balance the inputs so there's no difference. Well, the only way it can do it is by increasing the voltage on the output on pin 7, which via a resistor divider. So we have R3 and R2, these two resistors. A proportion of the output voltage will appear on pin 6. And the op amp will drive pin 7 up to such a point that the voltage on pin 6 matches pin 5. So if this circuit is working, we will find that pin 5 and pin 6 have the same voltage, which we can say should be 2.5, and pin 7 will have a higher voltage. If pin 7 was connected directly to pin 6 basically, then you could say that pin 7 will also be 2.5, but we have a divider, 120k, 220k, and we can actually work out what the voltage on pin 7 should be to give us 2.5 on pin 6. I can give a rough rule of thumb just looking at the circuit. So if they were both 220k, so we had 220 here and 220 here, then the voltage here on pin 6 would be exactly half of pin 7. So this would have to go to 5 volts to give 2.5 here. In our case, R3 is roughly, and it was just a roughly half of R2. So that means the voltage here will be higher than it would be if these were the same values. Okay, so if that's roughly half of that, then roughly 2/3 of whatever's on pin 7 will be here and 1/3 there. So what's 2.5 times roughly 1/3 more. Well, it's about 0.6, something like that. So we can say that the voltage on 7, we'd expect it to be about 3.1 as a very rough rule of thumb. Yes, I could get the calculator and do the maths. But what we can say is we should have the same on 6 as we have on 5 and something about 1/3 higher on 7. Okay? We have 2 resistors here. This is also part of the feedback. I have to say, this is putting 2.5 on here as well. So it looks like it's adding that to that, and this goes to the pot. Yeah, we can measure this, we can have a look. But the upshot is we should have a fixed voltage on one end of the potentiometer. Okay, and if I look on our version and on the original version, that should all be the same. So that's the first thing we're going to check. What's on pin 5, what's on 6, what's on 7, and what's on the potentiometer, okay? If it turns out that the voltage going into the potentiometer is the same on both, then the problem is going to be in this half of the circuit, okay? It's going to be in this half of the circuit. So this potentiometer can actually vary the voltage here on the wiper between 0 and whatever this fixed voltage is. And that feeds into this op amp, okay? It puts a voltage on here, pin 3. Again, the op amp will try to balance the voltage by putting the same voltage on pin 2. How does it do it? Well, there's a capacitor here, so that is not a direct current or DC feedback network because that capacitor blocks DC. The feedback is via the transistor to the voltage on the emitter. So the voltage on the emitter comes back into here, pin 2. What sets the voltage on the emitter? Well, it's the voltage across this resistor, and this is the current sense. So the more current we send in here, because we're driving the transistor harder, because the output of this is going higher, the more this is passing current, the higher voltage we get on here, and that comes back into here. And again, it will do the same thing. It will try to balance the system, so pin 2 and pin 3 are the same voltage as each other, and pin 1 will be higher because it needs to drive the transistor to put that feedback voltage on. So again, it all balances, yeah. So we have 2 halves of a circuit here, and I'm pretty confident you will see, even if you're not so familiar with op amps, how we can diagnose it. So let's look at this half first. Let's see then. I'll turn the load down to minimum, okay. Now, what do we have? So pin 5 of the op amp, this should be 2.5 volts. This is our reference, and it's 2.495. okay, so pin 6 should be the same, 2.406, so it's close. 2.495, 2.406. I'll make a note of those. Although it's close, I expected it to be closer than that, like basically exact. So on pin 7, 3.757. So sort of what I said, about 1/3 more than 2.5. Yeah, okay, that was right. So 3.757. So that puts on our potentiometer a voltage. What is it? Well, that end's ground, so this end is 0.227. That's low. Lower than I expected, but let's make a note of it. The middle one then should be 0 because I have the load turned down. So that is 0.227. Well, considering we have a 10k potentiometer here, and we have a 100k resistor here, and the 680, just ignoring the 680 at the moment because it's so small compared to others, it probably doesn't matter. That would suggest that the voltage on the 10k should be about 1/10 of the voltage here. which is about 0.37. Okay, that's allowing for the fact there probably isn't any current flowing this way, or very little. But let's have a look at the original version. We can make the same tests and let's see what we have. So with the load turned down, it's delivering about 2 milliamps. So on pin 5 we should have the voltage reference 2.496. The other one was 2.495, so that's practically identical. It's on 6. 2.422. So that's actually a little bit higher than the other one. So that tells me then the output on pin 1 is going to be a bit higher as well. Sorry, on pin 7. So what's that? 3.780. So assumedly the potentiometer is also slightly higher. Which end is it? This end. 0.235 compared to 0.227. So there is a little bit of a difference. While we're here then, let's have a look at the other op amp. So pin 3 is coming in from the potentiometer. And that's 0 because I have the current turned all the way down. What happens if I turn this all the way up? Okay, it's now turned all the way up. And it's 0.619. So pin 2, we should find the same sort of thing. At the moment the current is set practically to 0, so I'm expecting this to be 0. Okay. And we can have a look at the output on pin 1 while we're at it. It's also 0. And then we'll turn it up. So we turn it up. Output on pin 2 is now 0.588 and 1 is 2.487. So there we have it. On this one we can see the voltage 0.235 rather than 0.227 here. I mean, we're talking less than 0.01 of a volt there, to be quite honest, difference. I haven't measured around here yet. On the non-working one I will at the moment, but the 0.3867 is what's driving our transistor, okay, the base. And we have 2 of them. We can have a quick look at the base just to see what's on them, but because there's current flowing through here, it's going to be a bit lower than that. Let's have a quick look. Easiest place to measure then is just on the base itself. That's this yellow wire, so I've turned the current all the way down again. So that is basically 0 as you'd expect. That's basically 0. We'll turn it all the way up. And this is 2.076. And this is basically the same. So the transistors are balanced. Let's take some measurements now on our version. So I have the current turned all the way down. So on pin 3 we have 0 and we turn it all the way up. We have 0.251. No, 0.227, sorry. Okay, turn it down again. We go on to pin 2. 0 as you'd expect, turn it all the way up. 0.226, the same as pin 3. Oh, something wrong here. I'll show you. Turn it all the way down. Pin 1 is now 0, and we turn it all the way up. And this gives us 1.74. And on the base, 1.505. Slightly different because of these slightly different transistors. This is why we have the resistors in there. Okay, 1.50. This one reads 1.53. Okay. I can see where the problem is, I think. So here we have it. On both versions, the voltage on the potentiometer at the top is basically the same. Yeah, it's basically the same. And on our version, the voltage coming out of here will vary from 0 to 0.227. Okay, so it varies in that range. The most voltage you can get is the voltage that's coming in. Consider that an op amp basically draws no current on the input, you'd expect that to be the same. But on the working one, we have here 0.619, we have a much higher voltage. Yeah, where's it coming from? Because if you look at this schematic, there is nowhere that it can come from. Yeah, there's nowhere else it can come from. Because the voltage here is higher, the voltage on pin 2 has to go higher because it has to balance or try to balance. That means the voltage on the output has to go higher, so it has to drive the transistor harder and it has to pass more current through the resistor. Yeah, can you see that? So the problem is the voltage here coming in is low. And according to the schematic, it can't be any more than that, but it is on the good one. So I have somewhere a resistor missing, I think. I'm going to count the resistors on both to see if I have the same number of resistors. And if I do, I have one somewhere connected to the wrong place on our version. Let me have a look. This is our version. So let's count the resistors. We have more output transistors, so we have 4 of these 1K resistors. The other one has 2. But let's just count this as 1 resistor, as though we had 1 transistor. Okay, so we have 1. Then we have 2, 3, 4, 5, 6, 7. This is made of 2 resistors because it's a 2 meg and I don't have any 2 meg, so I used 2 1 meg in series. But we have 7 resistors. Plus, actually, we have 8 because that's the little one that measures the current. Oh, interesting. I see what's wrong with it. It's not what I thought at all. This one I have 2 here for the 2 transistors, but we count it as 1. Okay, so we say 1. Then we have 2, 3, 4, 5, 6, 7. And then we have the current sense. And look, current sense 0.05 ohms. Look at mine. 0.5 ohms. So basically, to get the same voltage coming in on our sense pin, we need 1/10 of the current than this one. What I've done is I put the wrong value resistor here. And that messes it up. That messes it up. I'm still not convinced why I have this here. I'm going to have a look at that. I don't see how that can affect that. So if it does, I'm really going to have a good think about how that could possibly happen. But with 10 times the resistor here, it's 1/10 of the current. I will get the same voltage on there that I would on the other one. So I need to change that first. Yeah, let's do that. I've changed the resistor here. I still don't understand the readings around that op amp, but this being 10 times the value it should be would definitely cause the sort of problem I was having with low output current. Let's see what it does now. So we switch on. And we have 8 milliamps or thereabouts. Okay, you can see it. So what happens if I turn this up now? Yeah, it's working. So I'm very interested to see what's going on with the voltages on this op amp on pins 3, 2 and 1. Okay, because I'm going to learn something here. Possibly. Okay, so I've turned it down. So on pin 3 now, I should have 0. Yeah, turn it up. What do I have? It's on full power now. 0.195. 0.195, they've balanced. 0.19, so I have lower readings all around. On the base, 0.1586. But it's working. Yeah, you can see it's working. I still think I have a resistor not connected correctly somewhere. I mean, I don't understand otherwise why they would behave differently like that. But it does work. That's interesting. I'm going to have a look on the other one. So I'm going to probe around from pin 3 on the op amp to see everywhere it connects to and then check with mine. Well guys, this is a bit of a mystery. I'm going to measure this again just to make sure I'm not actually cracking up, yeah, because it doesn't make a lot of sense to me. Okay, so that's the meter, you can see it. There's another PCB. Right, you can see it. So once again, we switch on. It's drawing a couple of milliamps. Yeah, load's working. Okay, put that way you can see it even. So the load is actually working up to about 3.1 amps. Yeah, and we can just, in fact, we'll turn it up, and we can go to pin 3 on here. Put it into volts range. What do we have? 0.61 volts. And on the end of the potentiometer, well, one end is 0.63 volts. I've got much more voltage on this one. Interesting. That has changed from what I was reading previously. I mean, I made a note of the readings previously. I don't know what's gone on there. You saw the readings. In the pale blue, you can see 0.235 on here, and it was working, and now it's 0.63, and it's working. I did actually look at the PCB. There is no error in this part of the circuit. You can see from pin 3 on the chip, just goes to the wiper on the potentiometer, and it goes to this capacitor here, 100 nanofarads, which goes to ground, and it doesn't go to anywhere else. Okay, so no voltage could get on there from anywhere else. No tracks on this side. It's a single-sided PCB. I'm starting to think, is it a problem with the op amp? I mean, I don't really understand still quite what's happening with this. So I've changed the op amp. This is the one off the other one. This is the one that was on this one. You can see they're actually the same chip, same number, same model. Okay. Once again, we'll just power it up. Yeah, 3.4 amps. You can see it there. Pin 3. 0.194. Maybe I've got a resistor value wrong. I mean, what it seems to be doing, and it is doing it quite successfully, is whatever the reference voltage that's feeding into the other side of the op amp, it's driving the transistors to match the output, and it's giving us a working unit in both cases, but with different voltages. Let me just check all the resistors to make sure I haven't made some other silly mistake like that. To do this, I need a USB-C to USB-C lead to connect the two together, because PD only works with USB-C. We'll switch it on again. Let's have a look. Yeah, it's doing 3.5 amps. I'll just turn it down a little bit. We have a flashing light on here in blue. I'll just drop this down. At the moment, this says we have 5 volts. Okay, you see 5.028 there. Okay, so let's hit the button on the decoy. Well, nothing seems to happen. Okay. Maybe this blue flashing light means something. Is our power supply not USB-C for some reason? Interesting. When I say is it not USB-C, I mean is it not PD? It says on it. It does say on it 5 volts, different voltages. You can see a mot on there. Okay, 9 volts, 15 volts. Let's just try another one. So this is a DJI power adapter we use for the drone. This definitely has PD, so we'll plug it in. I'll turn the load down for now. It's all the way down. We'll switch it on. Again, it's drawing some milliamps. Cap packet not received, may reboot. Okay. That tells me there's something wrong with the communication by the looks of it. I can load this one up and it didn't like that. It says entering PD. I can turn this one up. I can put a load on it the same as I could with the other one. Let's press the button. 9 volts, 12 volts, 15 volts, 20 volts. Let's just put some load on that. $33, $34, $36, 40 watts. And then he tripped out. I think the power supply actually tripped out. Yeah, everything went off. Okay guys, so you saw what happened there. At first I thought I killed the power supply, but I actually haven't killed the power supply. We switch on. Yeah, it's working fine. Okay. The problem occurred because this has gone short. I had a quick look. I thought it was all of the transistors that were short. Collector emitter, but they're not. I've been disconnecting them in turn and I find that this one is short. So one of my transistors went short. Okay. The other 3, well, at least don't read short. They may be damaged, but they don't read short. These are a Darlington, so you'd expect it to read like a diode junction, then like a higher voltage, if anything. Yeah, you see. Okay, and this one's short, as we know. Well, it's okay there. In fact, it's okay, effectively base emitter, it's collector emitter that's short. So guys, first of all I need to get some more transistors. Yeah, that's the first thing. Why one failed, I don't really know compared to the other ones, but you know what? That's going to make for an rather exciting installment 2. Yeah, so what do we know? We know we need to reverse this around, and we know that if we put too much load on things, something blows up. Not spectacular, but it did. So yeah, let's keep moving forward with this one. This video is plenty long enough. Thank you to PCBWay for sponsoring these videos. I hope you enjoy watching them. I look forward to seeing you all soon on another Learn Electronics Repair video. Ciao for now, guys.